In the last video, we talked about representing real numbers with Cauchy sequences, and we came up with the problem of when two Cauchy sequences represent the same real number. And I promised that in this video, we would resolve that situation, and we will. We're going to talk about equivalence of Cauchy sequences. So the big question that we're going to ask ourselves is, how do we determine when two Cauchy sequences that have different numbers in them, especially when do they represent the same number? This will lead us to a relation which we'll use the notation tilde for that describes when this happens. We're going to want that relation to be an equivalence relation, so one of the things we're going to have to do is review what equivalence relations are. You might not have seen those for a little bit. We're going to review equivalence classes, which are important groups of elements that come out of equivalence relations. And then we're going to use that to describe what an actual real number is. Spoiler alert, it's the equivalence classes. And then finally, we'll set up the proof that tilde is an equivalence relation. We won't go through the proof. That's something that you're going to do in the in-class activities, but I will set up what you assume and what you have to show for each one. So suppose we have Cauchy sequences a sub n and b sub n. The question is, how can we tell if they represent the same number x? Now, again, this isn't literal, this is kind of conceptual. Conceptually, when they represent the same number x, they both converge to x. Right? So that means as n gets large, an and bn should be getting close to x. But that also means that an and bn are getting close to each other. And then if we look at the difference between an and bn, an minus bn should be getting close to 0. So that suggests the following test for equivalence. Look at the sequence an minus bn. If it converges to 0, they represent the same real number, so they're equivalent. If it doesn't converge to 0, meaning it either converges to a different number or doesn't converge at all, then it's not equivalent. So let an and bn be Cauchy sequences of rational numbers. We are defining the relation an being related to bn precisely when the sequence an minus bn converges to 0. So I do want to point out that tilde is relation on the set of Cauchy sequences of rational numbers. So where this relation is defined is a set, and each element of the set is a Cauchy sequence. So, a couple of questions that you might be wondering. What are some of the important properties of tilde that we need in order to make this a reasonable way of telling when two sequences represent the same number? And how can we use tilde to define real numbers? So we'll get into each of those one at a time, though, one at a time. So, first of all, what properties should we demand of tilde? Well, first, and in some sense, all three of these things are kind of trivial observations, but they're very important because we need to make these things very precise. So first of all, the sequence an should represent the same number as itself. If we have a Cauchy sequence that represents two different numbers, that is an issue. That is a problem that we can't resolve. So we should have the property that an is always equivalent to itself, always equivalent to an. Secondly, if an represents the same number as bn, it should be the case that bn represents the same number as an. Again, it sounds obvious, but we have to state it to make sure it's true. Not all relations work that way. So that means if an is related to bn, then bn is related to an. And thirdly, if an represents the same number as bn, and if bn represents the same number as cn, then all three of those sequences should represent the same number. In particular, an should represent the same number as cn. And from the point of view of the relation, if an is related to bn, and if bn is related to cn, then an has to be related to cn. Now those properties should look a little bit familiar. That first one is called the reflexive property. The second one is called the symmetric property, and the third one is called the transitive property. And put them all together, and you get what is called an equivalence relation. So we need to prove that the relation tilde is an equivalence relation. If it's not, then it's not a good way of determining when two different sequences represent the same number. So let me define equivalence relation for you in case you've forgotten. It might have been a little while since you've thought about those things. An equivalence relation on a set A is a relation that satisfies the following three properties. First of all, the reflexive property. That means for every x in the set A, we have x is related to x. Symmetric property says that every time we have two elements x and y in the set A, if x is related to y, then y is related to x. And then the transitive property says if you have three elements x, y, and z in A, and if x is related to y and y is related to z, then x is related to z. And that's an equivalence relation. So we want our relation tilde on the set of Cauchy sequences, the one we defined earlier, to be an equivalence relation. So before I set up the argument for how you prove it's an equivalence relation, I want to show you kind of why we really need this. And the reason we really need this is we want its equivalence classes. So once we have an equivalence relation, that allows us to group the elements of our set into equivalence classes. So these are sets of elements that are all related to one another and not related to anything outside of the equivalence class. So here's a definition of how here's how we define equivalence classes. So again, we're assuming that tilde is an equivalence relation on a set A, and x is just some random element of A. The equivalence class that includes x is defined as, well, the notation we use is we put square brackets around it, square bracket x, is the set of all elements in A that are related to x. So that's kind of informally how we think of it. And I like using a team metaphor for equivalence relations. The two elements are related if they're on the same team. So this is like x's team, this equivalence class, right? So x is like, you could think of as the team captain, and bracket x is all the set of all players on x's team. More formally, bracket x is equal to all the elements y in A, such that x is related to y. So if xn is a Cauchy sequence of rational numbers, the question is, how do we interpret the equivalence class of xn? I know that looks a little bit weird because you've got all those brackets. Those curly brackets, those just contain the sequence x1, x2, x3, x4, x5, etc. Right? And then the brackets, the square brackets on the outside indicate we're taking the equivalence class of all the Cauchy sequences that are related to that representative xn. So all the Cauchy sequence in xn are related to each other. Actually, technically, they're all the ones that are related to xn. But then, once they're all related to xn, they're related to each other using the properties of equivalence relations. Another way of thinking about them is all the Cauchy sequences in bracket xn represent the same real number. Right? So what we're doing is xn represents a real number. The equivalence class includes everybody else that represents that same real number, which means that, our third bullet point, each equivalence class literally is a real number. Right? So the real number is represented by all the Cauchy sequences that represent that number. The equivalence class itself is the real number. So if A is the set of Cauchy sequences of rational numbers, in other words, it's a set and each element is a Cauchy sequence of rational numbers, we're going to find tilde on A such that an is related to bn precisely when the sequence an minus bn converges to 0. Then R is the set of all equivalence classes of tilde. That is our construction of the real numbers, at least the numbers themselves. We haven't talked about any kind of arithmetic or ordering. So all we need to do to construct the real numbers is prove that tilde is an equivalence relation, right? Yeah, we kind of forgot that detail, right? If tilde is not an equivalence relation, this whole thing falls apart. There are no equivalence classes. Nothing works. But don't worry, it's going to work. It's not like I get you this far and just give you a relation that doesn't work. But we have to prove all the properties. We have to prove the reflexive property. We're going to assume, and in order to prove that, we have to assume that an is a Cauchy sequence of rational numbers, and then we're going to show that AN is related to itself. Once you get it set up, it's going to be totally easy to prove that one. For the symmetric property, we're going to assume that AN is related to BN. Then we got to show that BN is related to AN. That is only going to be slightly more difficult than the reflexive property, so I'm guessing you won't have too much problem. The transitive property is going to be a little bit challenging maybe. You have to do a little bit of manipulation, computations, but I think you're up to it. You're going to assume that AN is related to BN, you're going to assume that BN is related to CN, and then you're going to show that AN is related to CN. Alright, but that's all the help I'm giving you in this video. Now it's your turn to work on those equivalent Cauchy sequences. Just click on the link below this video.